We have Alvaros Question on Jakarta coefficient and normalization. Okay, that's correct. Like maybe normalization is like a new thing, like you're maximizing and normalizing at the same time. I don't know, but normalization, great. Let me see. That sounds right. You're having the difference between Jacquard coefficient and dot product. The dot product's not normalized, right? So that does seem like a reasonable. Right, so we're talking about dot product, which is very useful and it can build into a lot of these, all the other methods, because you're really just combining the attributes of your two vectors, your two data points, right? So each of these vectors is supposed to be a data point. The dimensions D are the features describing it, and your dot product is going to kind of combine them all together. When it's binary, it's just going to be a count of the ones that agree, right? But if you take the dot product of a vector that's not binary, it's still going to be a kind of distance, not properly a distance measure, but a measure of how similar they are, right? Because it'll be higher if they agree. So Jacquard and these other ones are kind of quite different because really they're using this contingency table, right? And we're going to see lots of things like contingency tables over and over, especially even when you do the probability stuff this week. You look at here, they're talking about whether they agree or not, right? And so I guess, it's just, in this case, it's the value because we're talking about binary vectors. I always forget about that. If the value is literally 1, then they agree. If they're 0, then they agree. So you're really just counting how many times they're 1 or not. How many times there are each of these combinations, right? And so these different coefficients are, they're just, you could do any combination of this you want. These are kind of standard ones that get mentioned, but you're normalizing across not everything, right? So it's only normalizing things where there was some true, right? So it's a bit interesting that it ignores all the ones that are false, right? So that means they could be actually negative, but it tells you something about whether they have any similarity at all, like they have any agreement on the positive cases. So if you're talking about something where the binary vectors are a classification score, maybe, and you want to know how many times, it could be like a test for COVID, right? How much do these two tests agree or not? So every time they correctly get the disease, then you want to have a 1. So you want to say how often do they agree on positive diagnosis or correct diagnosis, maybe. Okay. So what else do we have here? We had another question on Piazza. I guess when I was describing it, I said something like, you're finding the distance between points in this matrix, but that was wrong, right? This matrix here is giving you rows, which are the rows are data points, right? As you go down, like every row here is a different data point, and the columns are dimensions or features that describe each one of them. Right? So it could be age, income, country, or something, if it's like a census data. And then we're talking about this distance matrix about them. We're talking about the distance between two elements, right? So the distance between row 1 and 2, that would be that distance. Distance between row 3 and 2 would be that. And since it's going to be symmetric, we don't need the other section here. So that was a thing I think I said wrong in the slide, but 1 minus SMC. What kind of distance would that be? The SMC distance. That's a good question. Because we're counting all of the ones where they agree, normalized by all data, right? So we're just talking about agreement normalized by how many data points there are total, right? So it would just be percentage agreement between them. And so if you talk similarity of how many ones and zeros they have in the exact same positions, it would be the actual distance between them, right? Because if you came up with if you have two vectors, I should make sure they agree somewhere. And I don't know if I have the same number. Yes, right. So they agree at least on a couple, right? So they're going to maybe have 3 agreeing plus and 1 agreeing, 2 agreeing on zeros. So you'd be getting that. So it'd be 5 over the length of the whole thing, and that'd be your coefficient. But if you did the distance between them, right, you'd be saying x minus y squared square root, right? So these are just going to be that way, and it's just going to give you an absolute value, essentially like this for binary numbers. That's all it is. No, we don't even need that, right? It's just the absolute value. So it is the distance. So when we say distance, we mean distance, like Euclidean distance. I think. Or, as we can also call it, the Minkowski distance, type 2, right? Because we're talking about distance metric. Oh, okay, right. That's on the previous topic, just figuring this. So the way I'm talking about it later, there is a related concept, which we'll look at next week in these videos, is the confusion matrix. And it's not exactly the same, because here we're just talking about how many times they had that value in it. In a confusion matrix, you're talking about whether they got it correctly, right? So if you have a data set of data points that are badly drawn X's and O's, right? And your function is something that, let's see if that works. It never works the first time. Why is that? I don't know why it's so hard to change color. Your function is something that puts all of these in the O category and all of these in the X category. You can come up with an accuracy, right? So what percentage correct did they get, right, in each one? And so in that case, then we'd be talking about each class, right? In this case, we say the classes would be 0 and X, and then you got it correct or incorrect, right? And then you put a count here, right? And that's a confusion matrix. So you use this to compute. So you can compute accuracy, you can compute precision, and many other things. So the table is similar in a way, but in this case, it's counting how many you got correct or incorrect as a classification, whereas a contingency table here is the literal values. These are the output values of the function, of the vector. Sorry, they're the range of the vector. Samrat's description is much more succinct than mine and correct. Confusion matrix is the type of contingency table where we have actual versus predicted charted. So all of this is related to, when we talk about distance, so now you have to use distance precisely. If anyone says, if you ever say distance comes out of your mouth and you don't mean this, then some professor is going to go, do you really mean distance? Can you show the triangle inequality on it? So you don't want to be afraid of the word distance to make sure it satisfies all of these rules. And they're pretty sensible, normal rules that, it goes both ways, that the distance doesn't change just by the direction that you're looking. Although sometimes physics does not actually work this way, which is weird. distances have to be positive, distances 0 is meaningful, and then this is triangle equality, which is really, Euclidean distance or Pythagoras' theorem, right? So if that relationship holds, not even strictly, but in a less than sense, right? So the distance can be, like Pythagoras says, that the distance you compute is equal, no, not to this actually, to something related to that. So Pythagorean theorem is stronger than this, right? But essentially you have to, the distance between the 2 points has to be less than the long way round, going block by block. And now we have all these fun ways of referring to distances, like the Manhattan distance, which is, it's like the blocks in a very grid-like city, like in Manhattan in New York. There's other examples. Toronto's fairly like that. If some of you haven't got to Waterloo, Waterloo is not like that. Waterloo is like angles and like this, and I can never understand where I'm going in Waterloo. I can understand it, but I can't understand north, right? Because it's north, and the same road will be east and west until there's like a little turn, and now suddenly it's north. Pretty crazy. If you haven't been here yet, it'll be fun. Manhattan, this is not useful here. And then k equals 2 for it. It's just our standard Euclidean distance. It is, right? That was our actual university. But you get to use this train line, which is great. And of course, there's malls. And then you can have higher Ks, and they're not sort of used that often in a way, but they, the Chebyshev distance does come up in a lot of theoretical things. We're essentially saying, what's the maximum difference between these values? And it can be used for bounds. So a lot of times in probabilities and proofs of things, you use this distance. But k equals 5 does not. I've never seen that come up really, but you could use it. These versions of it, calling it L, I already have it highlighted. Calling it L1 and L2 is a very common thing in machine learning papers. They would never say Euclidean distance, they'd say L2. And you'd be like, what do you mean? But to be fair, sometimes they're not using it as a distance. So you can use L2 as a penalty, right? So you can say, let's take all the data and take, right now we're calling it a distance, but let's take, you have some model, and this is kind of for future stuff, but you've got some model with your data and your labels and your parameters. Which we will, it's kind of what we're talking about this week and next week, I guess. And it's some function, let's just say it's some function that gives you that, and maybe it's a neural network, whatever. But then you can also say, let's put some penalty on it, which we use. It's called used for regularization. I don't think I would have mentioned this in any of the videos you've seen yet, although who knows. And the idea is you take this distance and you say, well, if the points are too essentially far apart, that's bad. So you should find a way to give me numbers so that they're close together, right? I guess in that case, we would be deleting, subtracting this, right? So you might have a penalty where you use a distance measure amongst the points to say, I don't want the points to be very far apart in your solution. So penalize them based on their distance. And you might use the L1 distance or the L2 distance because they penalize different things, right? If you think about it, L2, it has a square in it, right? So you're penalizing the distances even more, right? If they're very far apart, it's going to be even worse. And maybe you want to use a 3-1, right? You could do that too. You're penalizing points that are far away would be very bad, right? So there's kind of an intuition about how you can use distances for many things. Hopefully that helps. Is Euclidean distance the shortest distance between 2 points? I mean, it depends what you mean. Is Euclidean distance the shortest distance between 2 points? Are there any physicists here? Or theoretical mathematicians? Because I think in engineering sense, yes, maybe. If we have distance in absolute value, what do you mean if we have distance in absolute value? Now I got too much junk. No, Euclidean distance is when this equals 2, right? So it's this formula. But where all of the, where k equals 2. Hide on my notes. Right, so that's all it is, right? And so, right, because what is it if it equals 2? Now, of course, I can't, right? So then that becomes a half, right? And this becomes 2. And half is a square root. So you get Euclidean distance, which is the Pythagorean theorem, that the hypotenuse of the triangle is equal to the square root of the sum of the sides of it, the squares of the sides of it. We only put absolute value here because if k is odd, obviously, you get negatives and positives here. So that's not what we want, right? We really want this thing where, I guess I was showing you on a triangle here. We want it to be that you sum up all of the lengths of this triangle. If it's a 5-dimensional triangle or simplex, then that's what it is. You add up all those sides and you get a distance, which is across the hypotenuse connecting those points. And then that space, that line should be shorter than the sum of all of the sides of it. And so if there's negatives here, because it just happens to be in a negative direction in the numbers, like the numbers on that axis are negative, you don't want to subtract it out. You want to add them regardless. So it's absolutely valuable when it's squared. You don't need that. I don't know if that helps. Yeah. And so this other thing, I guess I said distance, right? Distance, if things are far away, right, then they have a large distance. So they are not very similar, right? That does not make it bigger. And if they are near each other, then it's similar. So I just thought that at the beginning, right? Distance is the same as dissimilar or unsimilar, or I guess you could just say different. Dissimilarity is a very fancier way to say it. They're different. If two data points are different, then they are far away, right? That's all. And so their distance is high. I guess we could say that too, right? So right, you could have a table like this where if dxy is high, and then you say distance, similarity. No, that was meant to be a header. If the distance is high, then if the number you get from whatever your form you're using is high, then the distance is large, I guess is a better way to say it, because the number is high, but the distance is large. English is funny. And the similarity is low. But if the number you get is low, then the distance is near or low, and the similarity is high, right? Because they're highly similar. It's just words. That's why math's better. Euclidean is this with a 2. Okay, so let's go back. Somebody wants to talk about kurtosis. We can look at that. Okay, so I gave you an idea of what this metric is used for, hopefully, but you'll see it used all over. So just this idea that you need to be able to compare the distance between points, and a point is a vector. So you just, if I give you 2 vectors, what's the distance between them? It might be useful. And it's going to be useful in training networks because you want things to be more similar. Like you've got data, which you're trying to match. You should try to be more similar to that. if you can. Confusion matrix. Somebody had a more general question. Yeah, the expectation and example assignments. Okay, so it was more about, should you watch? So the plan for these things, right, is like we're doing now. Hopefully this is going to be working for the course. Is that you watch the videos when you get time during the week, and then on the Monday after, or whenever the lecture is scheduled next week. Holiday here in Canada, so another item. And then we talk about it in the session, we talk about it online, and then you can study that, but you can also look at other materials as you're studying it and talking with people about the content. And then each assignment will be kind of based on, say, well, it's on the content from weeks, 1 to 3 or something. You'll know which ones it's relative to, and the quizzes as well. In terms of examples, we're going to try and be more clear about how assignments, like what we're expecting. I don't know if we're going to have a full example for it, but we do have there's a Python notebook starter for assignment 1. So it has a bit of an example, yes. Yes, next Monday is a holiday. That's important. It's the generic kind of day to celebrate the Queen and queenness and monarchy, because we're Canada. In Canada, it's the beginning of summer generally, so it's kind of barbecue holiday usually, and fireworks. So if you hear fireworks next Sunday, Monday, don't be scared or surprised. People often get fireworks and celebrate. You can only do fireworks on May 24th and July 1st. Another one? Well, New Year's, so 3 days a year in Toronto, Ontario area. I used to live in Vancouver, and they never have fireworks ever because the forest is very flammable, so they're just banned, except on Halloween, which is weird. So on that one, live session is moved to Thursday slot. So next week there won't be one on the Monday, there'll be one on the Thursday time slots, which is, I guess, Thursday 11 to same thing. Usually I'm just going to have that as office hours, so you can book time with me, but next week you have to be a live session like this. It's another thing I want to update on the thing. I'll move the Friday office hours to be in this slot so people can find it. Great.